Thank you, Sarah. It's a pleasure to be here and to have the opportunity to talk about one of my favorite topics, the solar cycle, evolution. And what I show you today is the recent decline we're seeing in solar activity and some of the interesting things that we have learned having the opportunity to observe the sun in a quieter state. Some were surprises, some were discovery or rediscoveries that you will see as I go along. And one of the main messages on my talk is that if you look at cycle 24, it's certainly different from the recent cycle, but in an historical context, it really doesn't look as peculiar or strange as many people think. So what I'm showing at the bottom is a plot of sunspot area as a function of time, going back to 1880, and I will talk quite a bit about sunspot area during my talk, because this is the longest record that we have available of physical measure of activity from the sun. There were some questions on the seminar on Wednesday. If some sunspot area is a good indicator of magnetic flux, and I'll try to address this in the course of my talk. And this really depends by the question you're trying to answer. So what you're seeing here is that starting at about 1940, we have been in a period of very high activity, above average. So most of the observing program of the sun from the ground and space were really started during a period of I've observed the very haptic sun. And cycle 24 is the first cycle when we see the sun in a weaker cycle, and you need to go back about 100 years to find a cycle that was just as weak as that one. So if we take a closer look to the recent cycle, this is again sunspot area as a function of time. I'm plotting in blue the daily values, and in purple you see the 3 rotation average. This is millions of the solar hemisphere, so sunspot area really covers a very small fraction of the sun. So I'm showing here an arbitrary line, and this is roughly giving you an idea of what the level of the previous two of the cycle 21 and 22 maxima were. So if we look at the number of days, we have a very large sunspot area which is above this arbitrary line. You see that we have a lot of these days in cycle 21 and 22, not that many in cycle 23. There is an interesting exception here with big spikes, which these correspond to the large active region that appeared on the sun in October, at the end of October 2003, and these were the sources of the halloween storms. And when you go to cycle 24, you really find that there are only a handful of days when activity was showing a large sunspot area. So in a more quantitative way, an interesting thing to notice also, if you look at the number of days when sunspot area was really close to 0, we have several of those days right at the maximum phase of cycle 24. So in a more quantitative sense, if we look at the value of sunspot area during maximum, we find that there is about a 27% decrease in cycle 23 compared to 21 and 22, and almost a 60% decrease for cycle 24. So we've seen a significant decline in activity, and especially in the recent cycle. Now, we not only have sunspot area for the total sunspot area variable, we also have data that tell us what the area and location of individual spots is. So we can look at the distribution of fluxes of spots over the sun. And what I'm showing here are 2 curves showing the number of spot groups as a function of spot area. And this was a surprise to me when I first looked at this plot. There is absolutely no scaling factor here. And you find that indeed cycle 22 and 23 track each other, the distribution track each other very nicely. There are almost no difference in the 2 distribution until you get to the very end in the tail of the distribution, which correspond to this very large spot group. So what this is telling us is that the main difference between cycle 22 and 23 is in the number of this very large sunspot complex. And you may say, well, does it really matter? I mean, these are only a few percent, and in fact, they correspond to about 2 or 3% of all spots that appear during a cycle. And this is certainly true, but this is a log-log plot. So there are not many of these large complex this large complex active region, but they account for about 20 to 30% of the total sunspot area that emerges during a cycle. So these are very big players in terms of the cycle determining the strength of the cycle, and also the polar field, as we'll see later. And these are also the longer-lived complex that we see on the sun. And another difference between cycle 22 and 23 is not just the number of this large active region, but the fact that most of these active regions appeared date in cycle 23, predominantly in 2002, 2003. So during the late maximum or declining phase of the cycle. Now, if we do the same kind of analysis for cycle 24, we find that there is a dramatic change in the distribution. This light blue shows the cycle 24. So we see a decrease of all in all sizes of spots in cycle 24, and a very significant one. And just to give you an idea, when we talk about large complex, what they look like, this is a large spot group, which is about 1,400 millions of hemispheres. So these are very large groups that actually are visible with naked eyes. Yes.
Did you correct that by the portion of the cycle that's been observed?
Yes, yes. So you are very right. In the previous plot, I'm showing the entire cycle, comparing 22 and 23. And here I'm comparing only the rising phase, the first 5.5 years. So I'm starting, for cycle 24, I'm starting in 2009. So I'm trying to be consistent as much as possible. We're still in the maximum phase, so we can't really say anything conclusive until the cycle is. And now, if I multiply this curve by 1.5, I can match fairly well the level here, but I'm still see a lack of large spark groups in cycle 24. So we're really seeing a large decline in activity. Now, you can wonder, well, is this change in the distribution really something unusual? Is something strange going on in cycle 24? And the answer is not really. I mean, if we look at the historical Greenwich record, you find that indeed weak cycles have fewer spots and especially have fewer of the larger spots. So what I'm showing here is the same kind of distribution analysis for cycle 19 and 12. 19 is the strongest cycle on record that we have observed. And cycle 12 is a very weak cycle. And in this case, I need to multiply by 2, not 1.5, to match these two curves. These here, but still, you see, I can't quite get to the level of cycle 19 in the tail of the distribution. So one thing that is interesting to ask is what is this means for irradiance. And if you look at the total solid irradiance record, you find very clearly the signature of the lack of these large spot groups in TSI. So this is showing the daily values in blue, and the red curves is the 81-day average. The large day-to-day variation is real. This is not noise in the data. And what you're seeing here, when the TSI decreases sharply, this dip corresponds to the passage of a very large spot group across the central meridian. So if you count the number of these, the days when TSI decreased significantly from the mean values, you find that there are more than 100 of these days in cycle 22 and only 66 in cycle 23. So the day-to-day variability that we see in TSI is very clearly showing this change in the spot distribution that we're seeing at the photosphere. However, if we look at the average curve, the two cycles don't look very different. And if you do an average of TSI during the 3-year maximum in 89, 91, and the 3-year maximum in 2000, 2002, what you're finding is that the value for TSI is remarkably similar, almost identical. So this was a surprise to me, and the reason is when you look at total solar irradiance, sunspots are not the whole story, of course. I mean, when you look at irradiance, there are both bright and dark magnetic pressure from the sun. So if you really want to understand the changes that we see in the radius data, we need to take into account both components. So what I'm showing here are 2 time series for sunspot area and particular area. And these are data taken from San Fernando Observatory. And you can see that they both show a decline in activity over the course of the last 3 cycles. And if you look just at the area, the sunspot area decline significantly more. This is very consistent with what I was showing you before was no sunspot record. And particular area declined about 19%. So these are, this is my friend Gary Chapman at San Fernando Observatory. It's a small observatory run by the California State University of Northridge. And they have this longest record of measures of sunspot impact that goes back to the 1980s.
Does that mean you have to be careful experimenting with TSI?
Yes, we do. In fact, I mean, we really don't know at this point because we only have sunspot area when you go back in time. So this is exactly the point we're making. And these programs, there are similar programs now running at Mauna Loa with PSPT and high resolution data. So with my friend Dora Preminger, we look at the faculae in the same way we look at the spots and ask what are the structure that changed the most during cycle 23. And it turns out that the change in the faculae was very similar to what we were seeing in the spots, where the largest faculae that decreased the most in cycle 23. So these are the kind of faculae that we found were fewer during that cycle. And these appear the brightest when you look at the sun at relatively low resolution because of the high filling factor. So this is important because when you look at irradiance, not only sunspot area is not enough, but facular area is also not enough. You really want to account the changes in the magnetic field in terms of the brightness of this individual magnetic structure. And so what these indices show are the sunspot deficit and facular excess. And they are computed going through an image of San Fernando, and they add every dark pixel with the observed contrast, observed brightness. And this is what it is. And for facular, they do the same. They go through an image and they count every the bright pixel with observed contrast. And when you look at these two, you find that the changes are very similar. So both of these two proxy changes of about the same amount. So it looks like for cycle 23, the changes in the facular contribution to irradiance and the sunspot contribution to irradiance were balancing each other. And this is probably why TSI didn't change very much. And this decline is continuing in cycle 24, but it's much more severe. So it's going to be interesting to see what's happened at the maximum of this cycle. And my suspect is that the fainter feature in the network will play an even more important role for this cycle in determining the variability. So we really need to know the magnetic flux and their contribution to irradiance for TSI and all irradiance. So far I've been stressing how the lack of large spots on the sun, but the fact that there are fewer large spots doesn't mean that the sun is now capable to produce strong magnetic field anymore. These are all data taken by Hinode SOT. These are high resolution images of spots, and I'm plotting them here because all of these spots have magnetic field of the order of 3,000 Gauss or more. So the sun still has some strong field, and this is still a normal cycle. Yes. Sorry?
And the last one, it says November 19, 2004.
Oh, yes. Sorry, it was 2013. This actually, and in fact, this is a famous spot. This is one of the, sorry. This is 2013, and you probably remember, this was one of the surprising spots of the cycle. This was very simple magnetically, but very large, it's extremely dark. And I don't know exactly what the values for these spots is, but some people reported 4,000 Gauss or more for this. It's one of the largest magnetic field we observed so far. So the sun this is a weak but normal cycle. We're very far from mountain minimum condition, as you can see. However, a few years ago, when we were going through solar minimum, there were quite a bit of worries about what the sun was doing, if a new cycle would even have developed. This is a plot showing sunspot number as a function of time. And you can see the minimum here between cycle 23 and 24 being for a very deep and very long minimum. Here I'm comparing the value of sunspot number for the previous three minima with the period from 2006 to 2010. And you see already in 2006 the level of activity was very low, continued to decline in 2007. In 2008 and 2009 in particular were extremely quiet years, where really not much going on the sun. So these are images of the sun in August 2000, around August 2008 and August 2009. These were some of the longer stretch when the sun was without spots. And if you count how many spots were on the sun during those years, they were present on the sun less than 30% of the time. And in fact, this is a movie, not a very interesting one, that goes through about 3 months of data, and you see there is really not much happening on the sun during those years. So this created a lot of worry in our community, and is that unusual that the sun goes through this very long and deep minima? And the question again is, the answer again is not really. Yes, we had a lot of days without spots in 2008 and 9, but if we look at 1954, before cycle 19, we actually had quite a few of those days as well. And if we go even farther back in time, we find minima that were even longer than the one we have recently observed. So what this plot shows here is sunspot number on the top, and each of these black vertical lines correspond to a day without spots. So you can see the length of this recent minimum compared to the previous one, but when you go back, you find that this doesn't really look unusual or peculiar in any way. So nevertheless, there was a lot of discussion, and still there is, about something peculiar going on the sun and the possibility that the sun is entering a Maunder minimum phase. A lot of this was driven by the observation taken at Cape Peak with the McMath First Observatory. And in 2009, there was a very controversial paper coming out in Nielsen reporting a decline in the sunspot magnetic field and a corresponding increase in the sunspot brightness. And their conclusion was that something was really changing in the physical property of spots. The spots were vanishing from the sun. And so their expectation was if this trend continued, there would be no spots after 2015. This is not very likely at this point, but then they changed their prediction and saying the spot will disappear by 2022. And this is a plot from one of the recent papers, and they're still suggesting that if this trend that they see in their data continues, spot will disappear pretty much with the next solar cycle and will go into a grand minimum. So what I'm showing here is spot brightness as a function of time and magnetic field as a function of time. And you see there is a significant change during this relatively short period of time. So a number of people, of course, look at these trend in other data sets. They've been using MDI, HMI, and more recently people have looked at INODE as well. And none of these studies really could confirm that such a trend in sunspot was visible. And we did a similar analysis as well with the San Fernando data. Of course, we don't have magnetic field, but we do have spot brightness, and the record goes back for a long time. So the first things we did was to plot the spot intensity as a function of spot area. If you do that for all spots, you find that there is a lot of scatter, but if you start averaging, you recover what is a well-known property of the sunspot, namely that the larger spots are darker than the smaller spot. There is nothing new here, but what is interesting is that you do that for cycle 22 and 23, and you see that there is really no significant change between these two curves for the two cycles. So we don't see a change in the properties of spots, and we have no indication that spots are getting dimmer. They seem to have the right intensity for a given area. So they cannot do that with the McMath data because they don't have a spot area. So what they have done was to look at the intensity as a function of time. So we did exactly the same. And this time we have a lot more data. We have 26,000 data points here that shows spot intensity as a function of time. And if we fit all this data, we really don't find any significant trend. It's almost impossible to distinguish this first order fit from a constant, a straight line, a constant intensity. So we find less than 3% change in sunspot intensity over time compared to, in the old 27-year time period, compared to the reported 2% change a year in the Penn and Livingstone data. So if I go back to their plot, you can ask the question, is this trend real? Well, let me show you what the new data look like for the McMath. This is what they look like. So you can see that starting in about 2010, there is really no trend in the measurements anymore. The trends seem to be gone. What is different in the data after 2010 is that at about the time they started to observe the spot in a very systematic way. So for every spot that was present on the sun, the magnetic field and the intensity was measured. While this record in the early years was not really meant to be a systematic survey of spots, and they only selected some target. And in fact, you notice that the intensity of data points here is quite low, but this is during the maximum phase. So you would expect a lot more spots be present on the sun in 2000, 2002 than in 2010, and yet we have only a few measures. Not only that, this is the level of, this level here is 1500 Gauss. And this is the typical magnetic field that we see in a small pore on the sun. And we know that there were plenty of small pore and small spot on the sun back in 2000 and 2002, but there is no measure at all at this magnetic field. So clearly they were not observing the small fields.
So the spot intensity and the magnetic field correlate?
They are very much correlated, yes, they are. So the darkest spots are also the one with the strongest field. And this is because the field inhibits convection and so makes the spots cooler and darker in terms of irradiance. This is all visible. Well, these are the infrared. These are the infrared measure. But it's the same in the visible. They have been the same relationship of work in the vision. So yes, the sunspot area, the brightness, and the magnetic field, they are all very much correlated. So largest spot are the darkest and the strongest field. So what we think is going on is that there is a bias in the urgent measurement toward the stronger field right here. So we look at our record of intensity for the same period of time. This is all the data from San Fernando. Then we artificially remove some of the small spot early in the early years to simulate what they did. And this is what you get. So it's very easy to introduce a trend in the data if you don't include all the spots systematically over the period of time. And so the consensus now is that indeed this reported change in spots is not a real change of the sun, but most likely an effect of the selection of the measure, of the spot contemporary measured. So another interesting thing that went on in cycle 23 and 24 was a symmetry between the north and the south. We had a very nice talk about that on Wednesday. And this was also one of the observations that was considered an indication of something strange going on the sun and possibly a new Maunder minimum coming in the near future. So if you look at sunspot area as a function of time again for the two hemispheres, now the north and the south, you see that while the times when the two hemispheres are out of phase are very common, starting in about 2006, the two hemispheres being consistently out of phase. So most of the activity at the end of cycle 23 was in the south, with very little happening in the north, and then the new cycle started first in the north and later in the south. So you can see here that the north reaches solar minimum condition in 2006, the south reaches solar minimum condition later, and then the north starts first and the south later. And if you look at the latitude of sunspot, you can get a good indication of what this difference in time between the two hemispheres here is. And you can see that the spot in the north are much lower latitude than the one in the south, which again is an indication of a time lag. And it's about a time lag of 2 years. However, if you look at the area under these curves, the north and the south has been about equally active at this point in time. So there is clearly a delay and there is a lag in the south, but so far we don't see significant changes in activity overall. There was a question if sunspot area is a good indicator for this asymmetry in the north and south on Wednesday, and this is the same plot for magnetic flux, and basically shows us the same picture. So yes, if we look at the asymmetry between the north and the south, sunspot area is indeed a pretty good indicator for that. And because we see the same changes in magnetic flux. So it is something to worry about, the fact that the two hemispheres has been out of phase for so long is somehow an indication that a Maunder minimum is coming. Well, the argument is that, I'm just showing now that the sun is very active both in the north and the south at present. This is a September, a couple of days ago, image from a couple of days ago. So the argument about this, that this asymmetry was strange or somehow indicating of something changing on the sun was that during the Maunder minimum there was a large asymmetry between the north and the south. However, this asymmetry in the Maunder minimum is only seen at the end of the Maunder minimum. So this is a famous plot showing the butterfly from 1660 to 1719 when the sun was getting out of the Maunder minimum phase, and you can see activity starts earlier in the south, and it takes a few cycles before both hemispheres become active. We don't have a lot of observation before the Maunder minimum, But if we look at the observation we have available, there's been a lot of effort recently to recover some of the observation. There is really no indication from what we can see of an asymmetry between the north and the south hemisphere before the Mandro minimum started. In particular, you see here, these are data points from, taken from the Velios maps for the Velios drawing in the year just before the Mandro minimum. And you don't see a big difference between the north and the south. Now, we are very lucky at Hanker. We have a copy of the Velios book in our library. And it's very interesting to go over some of the actually drawing made by Velios in 1642 to 1644. And you can see that as we look at the period right before the beginning of the Mandro minimum, we find that there were several sunspots on the sun. Some were quite large, and in fact, some were very large. This is a passage of a large spot group across the solar disk. And also, it's quite interesting to see in these drawings that in 1643, there are indication of a new cycle starting in high latitude in this drawing. You can see both facula shown as, he was showing the spots as, and also the facula around it. So we really don't know very much about how the Mandro minimum started. It's still something we really don't understand. And I don't think we are in a position to make any prediction about the Mandro minimum at this point. If we look at the historical record, we find that we had small cycle before, and the sun didn't go into a Mandro minimum. So this is sunspot number going back in time. And you see there were period of low activity at the beginning of the 1900 and beginning of the 1800 and 1900, and we are now going to, seem we are going to another period of low activity. So to recap this first part of my talk, the main point I want to make that yes, we are seeing a significant decline in solar activity in recent years, but cycle 24 appeared to be a weak but a normal cycle. There are fewer large spots in cycle 23. This weakening trend continues in cycle 24, which is giving us an indication of a weaker dynamo operating inside the sun. Strong magnetic fields are infrequent, but they're still present. We still have a large spot with strong magnetic field. And there is really no evidence for a change in the physical property of spots at this point. So we don't think sunspots are getting fainter. There are just fewer of them, which is normal for weak cycle, and this is why weak cycles are weak. So for the rest of my talk, I'd like to switch to a slightly different topic and show you the evolution of the polar magnetic fields and how the changes that we are seeing in solar activity at low latitudes actually affect the global distribution of magnetic flux, and how this weakening activity has affected the flux balance on the sun. So this is a plot showing the polar magnetic field. This is the time evolution of the magnetic flux between 60 and 80 degrees from the NSO observation, the observation at Key Peak. I'm using this region here because above 80 degrees the data become quite noisy, and using that as a proxy for the polar field. And you can see several interesting things in this plot. You see the polar field tend to be stronger near minimum. At around the time of maximum, they change polarity, and then they reform and change polarity again. So the first, what is clear is that during the last cycle, the polar field were much weaker than they were during the cycle before. In fact, we see a decrease of about 40% in the polar magnetic field. And not only the polar field were weaker, but we found that there is a lot more peaks of polarity in high latitude during 2006 to 1908 compared to 1996. And this is where we are right now. So the north started to reverse earlier than the south, which is consistent with the fact that the cycle started first in the north and later in the south. And then there was almost a triple reversal. I mean, it went from negative to positive, almost down to negative again, and now it's turning to positive. While the change in the south has been more gradual and it occurred later, but it's been more consistent. This is a magnetic butterfly from, again, NSO data, and it shows exactly what I was trying to showed you before, you can see the different polarity flux migrating toward the poles, and you have this event of positive polarity, and then there are some negative polarity flux going on, which make the north reversal quite complicated, while the reversal in the south has been a lot more consistent in time. Now, this is, of course, if you look at the polar field at very low resolution. In reality, if you look at the polar field in high resolution, you find that they are not region of weak field of about 10 Gauss, but they're actually formed by very small, strong concentration of magnetic field that have kilogauss strength. The polar reversal at the photosphere correspond to a very typical series of eruptions occurring in high latitude in the corona. So starting in about 2011, we've seen a number of polar crown, this dark polar region, which represent a neutral line near the poles, and we've seen a number of eruptions going on, which have continued until 2013, which is an indication of the slowness of reversal in the north, and same thing happened in the south, especially during 2013. So we can ask the question why the polar field were so weak during the last cycle. What was the main cause for that? We still don't know all the dynamics that is happening in the high latitude of the sun, but there is a lot of observational evidence from the evolution of magnetic field, and Gordon Peters is the one that has shown that in a more quantitative way, to my knowledge, at this point, about how the polar field evolved and how these changes are connected with the evolution of the magnetic field at lower latitude. You see these plumes of unipolar magnetic field, and the flux within these plumes is very highly correlated with the changes that we see in the high latitude polar field. And the flux in the plumes is very highly correlated with what Gordon calls the poloid of active region flux, which is a measure of the flux that is in the active region latitude, weighted by the difference, the distance in latitude between the centroid of the positive and negative polarity, which is another way to say the amount of flux that emerges along latitude and the tilt of the active region really contribute in large part to what we see in the polar field. And there may be unknown sources of also polar field changes that we really don't know yet. So there's been a lot of work in terms of trying to explain why the polar field were weaker using meridional flow changes argument. However, a lot of the recent observations are really giving us a very consistent picture that the changes in time of the meridional flow are mostly in the form of inflow towards active region. And they result in a meridional flow, which is meridional flow is a transport, is a polar world large-scale motion that we see on the sun. And we believe is responsible in large part for these plumes of unipolar field being transported toward the poles. This meridional flow is effectively faster during solar minimum when activity is low, and slower solar maximum when activity is high. And we have reason to believe that this is also happening for strong cycle and weak cycle. So in strong cycle, you will have a weaker flow, and effectively you are less, you are transporting light flux toward the poles, and in weak cycle, you are transporting more of flux toward the poles. So in a way, meridional flow acts as a balance the strength of the cycle. So strong cycle are less efficient, yes.
This cycle dependence of radian flow speed is that minimal is faster. What is the measurement? How do they do it?
This is just looking at the average profile. So because you have inflows, at the average profile of the meridional flow, you really have a flow. So I actually have a slide. Maybe I can.
It's not with seismology.
Yes, no, it's with helioseismology. I actually have a slide if I can. Let's see. Can get out of here. I can probably show you some of that. Let's see. I hope this will work. So if you look at the time and latitude variation of the meridional flow, these are average profile that shows the changes. Let's see. This is latitude, and this is the speed of the meridional flow, and this is when you subtract a mean profile. So you see there are these bumps in the flow, which correspond to these inflows towards active region. And this has been observed during several cycles. And they do change with the location of the active region. So this is a series of these profiles, longitudinally average for cycle 23. This is the same kind of profiles with from HMI in cycle 24. So what these bumps really do effectively is to slow down the polar world flows when they're present, and so near maximum. So this is in practice they make the polarity, the polar polarity transport less efficient during high activity. So there has been actually a lot of work about the discussion of this and how this can affect the cycle strength. So let me go back to my polar field. So meridional flow is acting probably in every just cycle the same way. So I don't think my personal opinion is not think the meridional flow was the main reason why the polar field were weak. And in fact, it should act to counterbalance the strength of the polar field. So the decrease in the active region is likely the main reason why polar field tended to be weak during the cycle, because we've seen a decrease in the in activity. We also think that the tilt of active region actually played a role. Here I'm showing again a butterfly diagram with this magnetic data from NSO, but not as much as before in the plot of Gordon. And I overplotted here the location of the very large spot groups. And if you see in this cycle, these large spots were distributed throughout the cycle, and some of them appear quite early during the cycle. But in the last cycle, they tend to be at the end of the cycle. They appear quite late and at lower latitude. So a lot of these active region likely had smaller tilts because lower latitude active region has smaller tilts, and probably they were not as important in terms of producing flux that could reverse the pores. So, and you see the weakness of the cycle right here compared to the previous two. So now if you look at the balance of magnetic flux over the sun, this is what it looks like. And what I'm doing here, I'm only looking at the large scale magnetic flux. So Matthias gave a very nice talk about all the magnetic flux that is in very small scales about a week ago. None of this is counted here. This is based on low resolution observation. So what I'm looking here is only at the large scale magnetic structure. And in blue, I'm showing, these are data from Kitt Peak again. I'm showing the total unsigned flux from 0 to 60 degrees. And this little green line here is a flux that is between 60 and 90 degrees. And if you make a ratio of these two, this is what it looks like. So at solar minimum, you find that a significant fraction of the magnetic flux in the sun is actually like a high latitude. This can be quite important. And what you see that in cycle 21 and 22 was about the same level, but is a much smaller ratio here in cycle 23. So activity at in cycle 23 was very low at solar minimum, but the polar field were also very low at solar minimum. So when you look at the balance between the high latitude and low latitude field, actually the high latitude field was weaker than during previous cycle. And these are the important implications for how the corona and the global magnetic field of the sun looks like in response to this magnetic configuration. So one of the things that people believed, and you'll find in many test books of the sun, is that at solar minimum, the sun takes a very simple magnetic configuration. They look very dipolar. This is because the polar fields are stronger and they're dominating in terms of the magnetic field. And this is eclipses showing exactly typical eclipse with a very dipolar simple corona streamer are visible at low latitude, and a typical solar maximum corona when you see streamer at low latitude. Well, now these minimum things look quite different. These are observations from Mauna Loa Solar Observatory taken between 2008 2009. So this is right during the period of time when activity at the sun was extremely low. We are in the deep minimum that I was showing you before on the cycle. Let's see if I can play the movie. And you can see that as you go across the year worth of observation, you don't really see the corona assuming a very dipolar configuration at all at any time during this year. So the corona look very different from the classical solar corona at solar minimum this cycle. And we can take a closer look at this, looking at a wider field of view. Now I'm using Glasgow, so I'm going to about 6 solar radii. This is for 1996. These are taken a week apart, so showing the evolution over a solar rotation. Again, a fairly flat, very simple dipolar configuration. In February 2007, the sunspot number was about the same, so we are already dropping to a level of activity which was similar. And you see a much more complex corona. This is just August 2008. This corresponds to the very boring moving that I was showing you before. Corona doesn't look dipolar at all. And this is 2009. Again, another period of extremely low solar activity. And this is as simple as the corona looked during the past minimum. As we moved from 2009 into 2010, activity started to pick up, and the corona went to a much more into a 4-sector structure, which corresponds to again the emergence of active region in the 2 latitude band in the north and the south. And these are just movies showing a very active corona during 2011, 2014, and this is a corona now. So very much a maximum corona, which is what we expect at this time of the cycle. So what is something unusual or something that never happened before? Well, we can go to the historical eclipse record and look at what the corona looked like during previous minima. This is a highly processed, nice eclipse image from modern times, and this is what the eclipse looked like in 1901. And this is a time when we had one of these long and deep minima similar to the one in 2008, 2009. So the shape of the corona can actually change from minimum to minimum depending on what, not just the global level of activity, but the organization of the flux on the sun is and how the ratio between the high latitude and low latitude magnetic field is. And this is also has an influence in terms of the distribution of coronal holes on the sun. This is, again, a pretty typical solar minimum corona in 1996, when you see 2 large polar coronal holes in the north and in the south. And in 2007, 2008, we still had significantly large coronal holes at low latitude present on the sun. And in 2009, this finally closed down, and we are left with a very small polar field, a very small coronal holes on the sun. And these are actually a significant implication for the solar wind and the heliosphere in general. So to be a little more quantitative, I'm showing you now maps of polar coronal holes. These are maps of the sun showing the longitude and the latitude here. It takes 27 days to make one of these maps. You need to wait for the sun to rotate. And the upper plots show the ultraviolet images, and the lower plot show the coronal holes. And these are derived not just by this image, but actually combining a number of images and magnetograms to try to define the boundaries of coronal holes. So in 1996, you have large coronal holes that extend down to 50 degrees or lower, and not very much coronal holes at low latitude at all. This is 2006-07. So you have much smaller polar coronal hole in these large and long-lived low latitude holes at low latitude. 2008 still look similar to 2007. And finally, in 2009, this low latitude coronal hole closed down. And you start to see some smaller and not very long-lived coronal hole forming at high latitude with the appearance of the new cycle. So the implications for the solar wind are significant. If you look at the solar wind in 1996, this is what it looks like. The average velocity was about 400 kilometers per second. In 2007, 2008, the average velocity wasn't very different, but you see that there is a very clear modulation of the wind in high-speed stream due to these large coronal holes in low latitude. So there is a lot more structures in the wind. And these things changed dramatically in 2009. With the close down of the low latitude coronal holes, we are left with very weak polar field and small coronal holes in the poles. And not only the velocity of the solar wind drops to a very low level, we are losing the coherence and the structure of the high-speed stream in the wind. And this is also implication for the interplanetary magnetic field, you see that not much was happening in terms of magnetic emergence at the sun in 2008, 2009, but the evolution of the large-scale magnetic fields and the closing down of these corona holes actually correspond to a period when the interplanetary magnetic field continues to decline in 2008 and reaches the minimum at the end of 2009. So we're still seeing an effect and the changes in the interplanetary magnetic field, even if the sun is not changing very much. So these were some of the finding and in some cases surprises, in some cases not real surprises that we've seen during the past 2 decades. And I'm running hurry here. This is my last slide. So cycle 24, it's not really so unusual. It looks very much like one of the cycles at the beginning of the 20th century, but the fact that the sun is quieter doesn't mean that all space weather is gone. We still have, and we can have some activity in space weather. So this is all I have to say for now. Mark?
Yeah, so is there symmetry in the cosmic ray flux of this cycle?
They see a record high cosmic ray flux in the data, in the modern era data. I mean, making the connection with the historical record is not as simple, of course. So how anomalous or how different this maximum is when you look at the historical record is not so clear. But so, yes, it was very high cosmic ray flux.
I've forgotten how the planetary field, interplanetary field, relates to
It's a surprise in a sense that if you go back to the record, you see that the level for the previous 2 minima were significantly higher, about 30% higher than what we're seeing in 2008, 2009. So this is indeed a very low level of the magnetic field. There are some reconstruction of the interplanetary magnetic field going back in time that Lise Valgar has done, and this value is not particularly anomalous in a sense that it's similar to what was seen a century ago, but again, these are reconstructions, so there are, of course, questions about how well they represent that. I mean, I think it's interesting that if you look at the interplanetary magnetic field now, the level actually never really went up very much, and it's not very different from what we have seen during a previous minimum.
What I mean is, just look at within one sunspot maximum, you see correlation between the sunspot number.
I don't have a plot for that. It's more complex than this. Yes, there is a general trend that you would see with the interplanetary magnetic field being higher, solar maximum, a lower, a solar minimum. But it doesn't follow strictly the sunspot number. Sarah has a nice paper on that. I mean, sunspot number, I mean, as you see, I mean, here sunspot number is really not doing anything. Not magnetic flux is doing anything. The sun is, there is very little evolution of magnetic flux on the sun, but the interplanetary field continues to decline. So the interplanetary field is a response of the open field on the sun, and it tends to have a minimum later than we see in the solar indices. But actually, there have been some questions. This is an interesting question. There have been some speculation of what the interplanetary magnetic field would look like if the sun went in a ground minimum kind of scenario. And there are even some people saying that maybe the interplanetary magnetic field in a mandra minimum would be stronger minimum than a maximum, because a minimum is when you build some coherent large polar field. And in a very weak cycle in maximum, you may not have a lot of flux on the sun. So what we're seeing in the recent, what I'm trying to say is what we see in the recent years correspond to what we're seeing during normal cycle and mostly above average cycle. But this relationship can change when you go to very different condition on the sun.
In your 2000 data, that active amplitudes ranging from 1 to almost 7 during the rising phase of cycle 22.
Yes, it's very similar. I don't think I have a plot on that, but yes, there is a very similar effect for cycle 24. So yes, we're going from a very, let me see if I can. Oops, for some reason I lost my. Oops. I don't think I can get out of here. I don't know what happened. I cannot really get to these. No, I don't think this is showing it, unfortunately. I don't think I have a plot for that. No, I don't. But this is a minimum phase of cycle 24, and you do have this tendency for active longitude showing only one active longitude in the minimum phase. And I don't have the progression of the cycles, but then as the activity started in 2010 and 11, you would see exactly the same increase in the active longitude that we have seen in the cycle before.
You showed one plot with the solar cycle variation of the average field below 60 degrees. How does it compare with the independent field? Do you do any correlation?
Well, it's hard to see. It's hard to see. I haven't really done the correlation, and it's hard to see here. But if you had to blow this 0 to 60, they kind of you would see. I mean, this is. It would look very much like the polar field. Let me tell you. I mean, maybe I can go back to this. So this is what it would look like. It would look similar to this plot. So if you look at the high latitude field, you would find that they peak at solar minimum, and their lower solar maximum. So when the polar reversal occurs, so there is now really a correlation with the.
So the independent field should be more correlated with high latitude fields instead of low latitude.
No, the high latitude field don't correlate very well with in the modern era. They don't correlate very well with the interplanetary magnetic field because they represent basically the open flux at high latitude in the polar corona holes. But the sources of the interplanetary magnetic fields are not just the polar corona holes. During most of the cycle, they are actually the low latitude corona holes. So there is not that correlation. So they are one component, a solar minimum, when they are dominant sources of the solar wind is coming from the edges of the polar corona holes, and then you find that they have an influence of interplanetary magnetic field, but not necessarily during the phase of the cycle.
So is that why so the low latitude could almost often evolve after the active region, and so there could be a lag between when you have a sunspot pattern between the active
Absolutely
region
true.
and then the formation of the low latitude chronoholes with a time lag, which then is the dominant solar maximum input to the solar wind.
Yes, there is, of course. Yeah. So all these things evolve on different time scale. Active region is in the form of a spot lasts only a few days to a week. Typically, magnetic flux can survive on the sun for many rotation, and the evolution of corona holes is on a much longer time scale. So there is
Try to predict independent magnetic field from the solar surface of the.
Oh no, it's a very complicated. It's terribly complicated. We have a lot of sources. I mean, and corona holes are one of those sources, but there is solar wind coming from a smaller region. There are CMEs and transient events, so it's really a very complex. This is a very, it's a simplification of what you see in terms of, large scale or longer time scale. But to predict the interplanetary magnetic field is one of the big challenges that we have for sure. There is.
So are you saying that coronas are not created independently from activity, or?
This is a good question. This is actually quite, we don't really know all about the formation of corona holes that they really form. The polar holes appear very clearly to be formed at the evolution of the high latitude flux. I mean, if you look at the, let's see if I can get here. So if we look at the evolution of the magnetic field, you do find that the formation of this unipolar region in the high latitude is actually very clearly the result of the evolution of the low latitude magnetic field. This is a dominant source for that. The low latitude holes, it's again, I don't think we really know. I think some of the corona holes do form from the decay of active region, and I have an example here. So at least some of the large corona holes are coming from decayed flux. This is what I was showing before to Masumi. This is the active longitude. This is the persistent activity at the same longitude. This consists of several active regions emerging rotation after rotation. And you see that at this active region decays, it forms two regions of predominantly negative and positive polarity. And this region right here, which is hard to see in this in the screen, but it's mostly negative, is where these large corona holes form. So you can also see that there is not much where this flux around it that can reconnect with. So in some cases, the decay of these large active complexes form these large patches of unipolar field that doesn't really have anything to connect with and ends their life in the corona hole. But do all the corona holes form this way? I don't know. Some do, for sure.
There are kernels created from just the planet sun. They aren't necessarily created from between active regions.
It's a very difficult question to answer because, again,
I just wanted to hear that it's not all from.
I don't think we know. I mean, what we know is some of the decayed flux from active region ends their life in corona holes. If the vice versa, if something has happened on the sun, I really don't know the answer for that. I don't think we can establish that from the observation we have right now. Any other questions? Thank you. Thank you very much.